5.8 is going to have us do some exponential growth and decay problems. These would mirror the ones that you did in intermediate algebra as one of the applications of exponential equations. We can use logs to unlock them as well, and so they're usually put in a similar place to this at the end of a discussion of exponential equations and logs. And so as we look at a problem, I was going to type it out, but then I realized I couldn't type out the equations. I didn't have the editor to do that. And so here's the first question that you'll see in the homework. They'll talk about a radioactive material. So in this case, they say, well, let me say Wayne 47 is a radioactive material. That decays at, according to the function. And then they're going to use A of t. A stands for amount. The amount at time t is equal to the initial amount, A sub 0, E, and then the general one has kt, where k is either the growth or decay rate. It's a decay rate, so it's going to be a negative, right? So something decays, it has a negative growth, negative 0.024 for t. Sorry, just making sure I'm seeing that right. And what am I looking at? I'm looking at your homework. And it says where A0 is the initial amount present, and A represents the amount after time t in years. So t is in years. T can be in days or whatever. It really just depends. And most radioactive material is in years, but I have seen some in thousands of years as well. So shouldn't say that. Okay, so that's the equation that we have. And then they say this: assume a scientist has a sample of 500 grams of Wayne 47. Okay. Then they're going to ask you to answer some questions. So their goal right now is to make sure that you have familiarity with this formula, that the numbers make sense and the variables make sense to you. So this natural number E is coming up here, and that is not a mistake that it's being used. So, for example, we used to have a nuclear power plant out here in Sacramento area, Rancho Seco. Years ago, we voted to shut it down. I was a kid at the time. Everybody was worried about Chernobyl and other high-profile types of radiation leaks. And so they said, we got to get rid of that. It was a good, cheap source of power that I'm sure now we wish we had kept, because it was relatively safe. But there's a bunch of radioactive material that's still under there. It was just all concreted in and pipes cut and concrete put in. And it's just decaying because it decays over time, right? It only loses a little bit. Sometimes with radioactive material, it takes like thousands of years in order just to cut it in half. So assume a scientist has a sample of 500 grams of Wayne 47. A, what is the decay rate? Of Wayne 47, right? Well, they just want to make sure you understand information. The decay rate is, they want it as a percent. It is 2.44%. Do you see that happening? The decay rate is actually the K value. If you remember from intermediate algebra, we used to say e to the kt. It's the number that's here. This is either the growth or decay rate. The only reason it's decay is because it's negative. So they're not going to put a negative on this 2.44. But sometimes they will. I think it will accept both answers. I am looking, and they are putting a negative on there. Usually I've seen it where it's not the case, but a negative one, they do want you to stress that it's a negative growth, but that's interesting. Okay, so how much is left after 40 years? Okay, so they'd have 500 grams. How much is left? Well, this is where we use our equation. We know A of t is equal to A sub 0, e to the negative 0.0244t, and t is in years. And so what do we know? Well, we want a time of 40. We have an initial amount of 500, e to the negative 0.0244, and the time is 40. So we're just figuring out this right-hand side. What are we going to do? Just grab our calculator. 500 times. Get your e to a power on your calculator. So there's no way to do this by hand. You'll need a calculator. There's my e button. I couldn't find it at first. Then I'm going to type in negative 0.0244 times 40 in those parentheses that it formed. And I'm looking at 188.407. It asked me to round it to the nearest whole number, so I'm going to say 188 grams. So after 40 years, we'll have 188 grams. C. When will only 100 grams be left? Certainly that's greater than 40 years. So what do they want to know? They want to make sure that you know this formula. So here's the formula. Let me highlight it. This is the in general formula. Do you know what all those variables mean? Well, what do we want? We want an amount to be left. What are we looking for? We're looking for when. We're looking for time. So the amount that's left is 100. I started with 500, and I got e to the negative 0.0244 t. We're going to divide by 500, and I'm going to get, 100 divided by 500. So we're going to solve this exponential. We're going to get e all by itself and get 0.2 is equal to e to the negative 0.0244 t, just like you did in intermediate algebra. So what's the best way to solve this? The best way to solve this is to maybe turn this into its log statement. Log base e of 0.2 is equal to negative 0.0244t. If you just went through that first statement, remember when you were doing things like 3 squared is equal to 9, write that as its log? Well, that's log base 3 of 9 is equal to 2. We just did the same thing. We could also apply logs to both sides. There's a couple of ways for somebody to visualize this. But what if we just said, let's just change this to its log statement. Log base e of 0.2 is equal to the exponent. Why do that? Because now I can get to the exponent by dividing both sides by 0.0244, but negative, right? So now we have ln of 0.2 divided by negative 0.0244 is equal to t. Some great algebra here. So now what do I do? Grab my calculator. ln of 0.2 divided by let me get the negative in there. Negative 0.0244. And we're looking at a time of 65.96, and it just keeps going years. Now they want it to the nearest whole number, so we're going to report 66 years. In 66 years, we'll have 100 grams left. Great. And then they want to know the half-life. So they're saying, what is the half-life? Often we talk about items in their half-life. What is the half-life of Wayne 47? Well, we can use our formula. Remember, our formula is not a sub 0. Let me back that out of there. A sub t is equal to the initial amount, e to the negative 0.0244 t. Now we knew our initial amount, so we might as well use that here to help everybody out. Now what's half of it? That's what they're asking. The half-life is a time. So asking for the time to get half of it. Half of it is 250. So it's just like the last problem. Now, it wouldn't have mattered if I started with 500 or a million. Whatever number I pick for half, the very next step is to get e all by itself. That's how you solve exponentials. You get the value by itself. And we get 1/2. For the sake of writing, though, I'm going to write that as 0.5 is equal to e to the negative 0.0244t. So what am I going to do next? Well, this time I'll show taking the ln of both sides. It's going to be essentially the same thing. ln of 0.5 is equal to ln of e to the negative 0.0244t. So I'll show the other way that it's often explained. So the first way that I did it back here, I just translated an exponential into its log statement, always works. Or you can apply ln's to both sides. This is ln of 0.5, and the ln and the e cancel because they're inverse functions of one another, and we get negative 0.0244t. And so it looks very much the same as the last problem. There really is no difference. And so what's t equal to? Well, ln of 0.5 divided by negative 0.0244. And I'm getting 28.407. They want me to round to the nearest 10th of a year. And so that's 28.4 years. So every 28.4 years, we have half of what's remaining. So in 28.4 years, when we start with 500, we'll have 250. 28.4 years after that, we'll have 125, and it's so forth and so on. That's problem one, right? All those parts were to that first problem, but so much was done there. Now you're wondering, how many of these problems are there? There's only 4. Right? They're all very repetitive. Are they always this long? No, not necessarily. Here's the next problem. Okay. A popular colony of mosquitoes obeys the law of uninhibited growth. So the law of uninhibited growth is, sometimes they use an n instead of an a, n being number of. N of t is equal to the amount you start with, e to the kt. That is the law of uninhibited growth. Okay, so question says this. And so notice, but let me just take a step. Notice that that's exactly the same equation as what we've been using, this highlighted one right here. The k in our case, because it's growth, is going to be positive. When I say k, this is our k. Everything else is the same. This E is there as well. So we have this mosquito colony. So what does it say? The population of a colony mosquito obeys the law of uninhibited growth. If there are 1,000 mosquitoes initially, and there are 1,700 after day 1, what is the size of the colony after 4 days? So 1,000 initial, 1 day later, there is 1,700. How many in 4 days? We're almost getting to mosquito season, and they do multiply quick. Now, time can be whatever they're talking about. So previously with the radioactive material, Wayne 47, it was in years. Now with the mosquitoes, it's in days, right? Mosquitoes don't live very long just in general. So it makes sense that it's going to be days. Well, perfect. Let's just take a look at what our equation is. N sub t is equal to 1,000. E to the kt is where we're starting, because that 1,000 is our initial amount. The initial amount is always the sub-zero one. So hopefully you're not seeing that as no. That right here is n sub 0. Okay, so it's a little subset of 0. Okay, so we don't know what k is. They didn't tell us. That's why they gave us this piece of information, so that we could solve for it. So what do we know? We know when t is 1, we get 1,700. Let's make that happen. So 1,700 needs to be equal to 1,000 e to the k, which we don't know, but the time was 1. So 1,700 divided by 1,000 is 1.7 is equal to e to the k. Well, let me just use the definition of logs. That means ln of 1.7 is simply equal to k. Now, I don't know how many decimal points we should round out to. Let's take a look. ln of 1.7 is 0.53062851 is equal to k. Let's do what they modeled before, 4 decimal places. Maybe that's what they're doing. So now this part right here was side work to help me. What do I know right now? I know my formula even better. N sub t is equal to 1,000 e to the positive, right? There was a positive growth of 0.5306 t. Where if I plugged in 1, I would get out my 1,700. Great. They want to know how much I'm going to have 4 days later. Let's figure that out. So that now I have my equation. In the previous problem, they gave it to me. Here, they gave it to me in a way that I could figure it out, but they didn't just flat out hand me the growth rate. Very normal to do that, because how we get growth rates is off of observations, not out of somebody saying, this is the growth rate. Okay, so what are we being asked to do? Find n sub 4. Oh, no problem. That's 1,000 e to the 0.53064. And what is that? Well, our calculator tells us 1,000 times e to the 0.5306 times 4. Close that parentheses. And I get 8351.156 mosquitoes. Okay, so 8356. Now, it's asking me not to round until my final answer. And I am getting something slightly different. So let me go back to the ln of 1.7. That was 5306. Let me just keep all the numbers because it's making sure to tell me not to round off at all. 5306, 2851. Actually, I don't even think that's right. 5306, 28251 T. So let me try that. Now, you're thinking, well, that's crazy, Jensen. How long is it taking me to write the next the next numbers? Nothing. Taking me very little time to do that. Let's see if it makes a difference. If I take 1,000 times e to the, and I'm going to type it in, 0.5306. It would have been done before. 28251 seconds times 4. And look at this. It made a big difference. The answer coming out of my calculator now, 8352.099998. The right answer is 8352. And I was going to put 8351. Don't round off that growth rate. That's what we learned from this example. How long will it take? How long will it take until there are 60,000 mosquitoes? Okay. The last part is, I will need 60,000 mosquitoes. Well, you're starting out with 1,000, e to the 0.5306, 28251 t. 60,000 divided by 1,000 is 60. Is equal to e to the 0.530628251 t. Take the ln, right, or put it in its log statement, is equal to 0.530628251 t. And you're going to divide by 0.530628251 to get t all by itself. So we don't complain about it because it's circumstantial. We just let it ride. ln 60 divided by 0.530628251. If it bothers you to have to write down all of those numbers, you can find a way to store it in your calculator. You can look online and it will tell you how to make storage places where you can recall that. I just know it would take me too long to figure that out, way longer than just typing in 28251, right? And what do I get? 7.71 rounded to the tenths like they're asking is 7.7 days. In 7.7 days, almost 8 days, we'll have 60,000 mosquitoes. Awesome. That's the type of work that you're doing in this section, is going over these types of things. I think the other two that remain are very similar in there. So yeah, we have like the half-life of carbon in there. Okay. Yeah. So I think you'll do okay with the last ones as well. There's good models out there, but these are good models as well. So it takes a little bit of time, but you only have 4. But it's very good to get familiar with this because so many things in life operate off of exponential growth and decay. All right, thanks so much.